have a little bit of time for me to answer your questions, if you have any questions. Okay, so now let's look at section 5.2b. Now this one is volume by simple cross sections, and even though it's a little bit different, but it shares the same basic formula. Essentially, the cross section is not a ring, but it is going to be some simple shape, like a square or a triangle or like a part of a circle, or it could be a something, but generally some simple cross sections. So that's what the section is. So now let's look at this one more time. The general volume formula. How does it look like? The general volume formula is this. What is it, right here? Let me use the red marker. So the volume is equal to this right here, and it's going to be basically the sigma of what cross-section, limit sigma of a cross-section area times the delta x. And so this eventually becomes an integral, where A of x becomes the cross-section area at x. Now, if you cut into dy slices, then of course the cross-section will be in terms of y. So A of y and then times dy. Once again, the slicing direction is very important here. So you have to make sure that you get everything accurate. You know what, this section has a lot of details. You have to get every detail perfect. Okay, I'm going to start from example of 1. Let's see, example 1 is actually what? The pyramid. Let me come back to this pyramid later. So let me start from example 2. I would like to start from example 2, all right? So let's do that. Example 1. Example 1. Okay, let me skip example 1 for now. It's about the pyramid. And so let's start from example 2a. Example 2a. Okay, so example 2a, what is that? Example 2a is this. Find the volume of the solid whose base area is bounded by y plus x squared and y plus 4, and whose parallel cross-sections perpendicular to the x-axis are squares where one side lies on the base. Okay, so when you look at these questions here, the first thing is, initially it's kind of hard to understand what they even mean by all this, right? So now let's try to slow down here. Let's try to understand what kind of solid they're talking about. So first of all, what is this here? Find the volume of solid whose base area is bounded by this. So now what we have is, why don't I draw the xy plane? So the xy plane is going to look like this. XY plane, XY like this. And then what is the curve here? The base area is bounded by y plus x squared. Y plus x squared is this right here. Yeah, y plus x squared is this. Y plus x squared, and y plus 4 is this. So this line is y plus 4. This line is y plus 4. And what is this? This curve is y plus x squared. So it looks like the base of the solid is this region right here. This is the base of the solid right here. This region right here. Okay, or now. Now let's go back here. Find the volume of the solid whose base area is bounded by y plus x squared and y plus 4. Okay, so we got that. And whose parallel cross sections perpendicular to the x-axis. So this is the x-axis here. Now, what kind of solid is this? When we take the parallel cross sections perpendicular to the x-axis, that means this is the x-axis right here. That means we'll be cutting it this way, cutting it this way. That's why we have to cut. When you cut it this way, what do we do? What do we get? Whose parallel cross sections perpendicular to the x-axis are squares, where one side lies in the base. What does that mean? So if you cut it like this, then this segment right here will be the base. And then the square is actually going to pop up like this, if you like. Maybe I will draw this popping up in a different color. How about if I draw this in blue, so that they stick out like this. If you have this, then it kind of sticks out like this. So these squares are not flat; they're actually standing up, towards us, standing up vertically. And so when you do all that, what kind of a shape do we get? That's kind of hard to imagine. So let me redraw this: x here, y here. By now, I'm trying to draw this in a three dimension. X here, y here, and now what is this? Y plus 4 is this, and y plus x squared is this right here. And then now what is this? A parallel cross section perpendicular to the x-axis. The x-axis is this. That means if you cut it, and all the slices will be cut perpendicular to the x-axis, that means we cut it here and here and so on. So if you now have this right here, like this, then how will the cross section look like? The cross section is going to look like this. Let me change color again. A cross section is going to stick like this. And then if you have a segment here, the cross section is going to stick up like this. The cross section perpendicular to the x-axis will be squares whose base lie on where one side lies in the base. So it is kind of hard to visualize what this is. Okay, it's kind of hard to visualize how the thing even looks like. So it looks like it's going to, if we connect that, we might connect here, and then we might have to connect here, and then the cross section is going to look like this. So it's kind of weird shape. But when you take a cross section, it is going to be a square like this, and the cross section will be perpendicular to the x-axis like this. Okay. Again, I still, don't know how to visualize, put this in Desmos. I think Desmos they can do it, but I'm not there yet, so I'm in the process of learning this. I think the three-dimensional stuff, they have lots to plug in. It's not like a two-dimensional graph, and so they have to put in a whole lot. So we have to spend a lot of time even typing in all the sources, okay, the quotes. So anyway, right now, I think this is good enough. It's kind of hard to visualize, but that's what it is. So here's the base. That's the base right here. So this is the base right here, and then the shape is sticking out. But when you cut it perpendicular to x-axis, then the squares are going to stick out. That's what it is. So the cross section of x will be what? Will be squares. Okay. So now let's do this again. So now this time, now how do you do this? So now let's go back again. So first, when you have a problem like this, x-y axis, the first thing is to identify the region. So in this case, this is the region we have identified right here. The area is this region right here. Bottom curve is y plus x squared, and the top line is y plus 4. So this is y plus 4. So we got that one. Now this is the x-axis. Now, it says here, parallel cross sections perpendicular to the x-axis is this x-axis, and that means we are going to cut it here. That means the slices will look like this. Each slice is going to look like this right here, so that each slice will be sliced in dx slices. So now what we want to put right here, if we cut it here, and now what do we get? We actually get a square. So this is now the cross section. So this will now be what? A of x. The cross section of x. Let me change my color here again. Let me change to black. At this cross section right here, the cross section is x. Now at x here, what is this point right here? So in this case, what is the main axis? The main axis is x-axis, which is y equals 0. If main axis is x-axis, it will be slicing perpendicular to x-axis. Therefore, the slicing direction will be dx slicing. Again, we can call the slicing direction the vertical direction or the horizontal direction, but the horizontal vertical is very, very confusing to me, so I decided to make it super clear. So I call it either dx slicing or dy slicing. Those are the only two directions we'll be learning. Okay, so we only study dy slicing and dx slicing. Therefore, if it's dx slicing here, that means everything has to be written in terms of x. That means we now want to get a at x, and this is of course dx. Now, if it's dx here, now we get this point right here. What is that point over there? That point is x comma y. Y is equal to x squared, so we can write this as x squared. If the slicing direction is x, dx, that means everything has to be written in terms of x. And now, what is that point over there? The top point right here, or that point, the slicing direction is x at x. It's a cross section of x, therefore, the x coordinate is x. And what is the y coordinate? That will be 4. So now we now have a segment right there. It's a cross section of x. That segment right there is actually this segment right here. And what is the length of the segment? That will be the distance between those 2 points, the length of the segment over here. So we take to get the length of the segment, we always go top minus the bottom. So that will be 4 minus x squared. That's a square, so this y will also be 4 minus x squared. So the main axis is the x-axis. That means we'll be cutting into slices perpendicular to x-axis. And so the slicing direction is now dx. So what is a of x? A of x turns out to be 4 minus x squared, 4 minus x squared, and then square. That will be our a of x. And so that's it. Now x ranges from where to where? X is ranging from here, from minus 2 to 2. See the slices right here? The slices range from x goes minus 2 to 2. And so the limits are from minus 2 to 2. This is a of x, dx slicing, and it's a of x. And what is a of x? A of x, I just wrote right there. That will be 4 minus x squared, 4 minus x squared, and then square. Get this right here. So that is integral. Anybody has any question here? Now note that here, you know what we see here? We see this. We see that this guy right here, the integrand right here. Let me see the integrand. Okay, let me use green here. So this integrand right here, this is a 4 minus x squared and then quantity square. This is actually an even function. And then if you look at the interval, say, oh, from minus 2 to 2, on a symmetric interval. Oh, so it looks like we can actually apply a theorem. You see we can apply that theorem? The theorem is the definite interval on even and odd functions. Remember that theorem, which we studied a few days ago? We've seen that a few days ago. So if you look at the symmetry here, we have an even function. And by the way, in section, on this section, many of these intervals will actually have a form like this, where the integrand is an even function and will be on a symmetric interval. Very, very common on this section here. So in this case, I think to make our life a little bit easy, what we're going to do is this is actually equal to 2 times the integral from where to where? Not from negative 2 to 2, but from 0 to 2. And then we just keep everything the same. 4 minus x squared, 4 minus x squared, and then what? And then square, and then dx. When you compute, you can actually compute this, and I think this will be a little bit more easier to compute, easier to calculate. Okay, If you just want to calculate that interval right there without using this even and odd property of definite interval, then fine, you can just do that, you'll get the same answer. But if you do it this way, there will be a lot of negatives. The chance of making a calculation mistake is, I think, significantly higher. Okay? So you take your risk. But whenever we want to simplify, this I think is much easier because the lower limit is 0 here. So when you plug it in, zeros are very easy to plug in. So calculation-wise, although it may not look like it's a big difference to you, but when it comes to calculation, you can actually do calculate much, much faster. Yes, because of this even property. Any questions here on example 2a? Any questions here? You save this and now clear this. Now let's go to example 2b. Now here, I call this example 2a and example 2b here. Why did I call this guy example 2a and example 2b? Are there any similarities between the two problems here? And the answer, yes, almost the same. You know the difference between example 2a and example 2b? When you compare the two problems here, there's only one single letter difference. One letter difference is going to completely change the problem. This is telling you that you have to read every problem, every letter, very, very carefully. Again, one letter difference is going to give you a completely different solid. When you compare example 2 and example 2b, what is that one letter difference? Can you figure out? What is the difference between example 2a and example 2b?
The x and y-axis?
That's right. X-axis and y-axis. In fact, there's only one letter difference. Here we have x, and this guy 2b has y. Everything is exactly the same. But if that one letter changes, you know what happens? The entire solid changes. And then the answer is completely different. Okay? So if I give you a problem like 2b, and then some of you will be doing 2a, do you think there will be a penalty? Yes, there will be. If this is a 15-point problem, and you do the other one, the deduction might be at least 7 points. You lose half of the problem right away by misreading that one letter there. So I'm letting you know, one letter, yeah, that will cut down half of the problem because you are now doing a different problem, a different solid. The interval will be different. You are doing a different problem than what I intended to give you. So therefore, the penalty is severe here. So what I'm telling you is, please read the questions extremely carefully. You cannot afford to make any mistake on misreading the problem, all right? Again, one letter difference, literally one letter. As you can see, one letter difference here is going to completely change the problem. Same thing with like y equals 4. How about if it's like y equals -4? If you have minus sign anywhere, then now that will also change it too. So one character, one letter, or one character difference will completely change the problem. So now I'm going to scroll this over here. So now let's look at example 2b. Let's see what we have here. Again, very, very similar, but completely different problem. Well, not completely different. The initial work is the same, but the solid is completely different. Solid is, once again, it's completely different here. So let's look at example 2b now. What is this? Find the volume solid. Okay, so we get the same thing. So it looks like we have is this. So we have is this right here. So we have the y-axis, x-axis here. And what is it? We have y equals x squared is this guy right here. And we have this guy right here. And we have y equals 4. So far the same. So once again, we have what? Y equals 4 here. And this curve is y equals x squared. So far so good. So far the same. And then now, when you have the space region right here, and then of course you have to identify the region here, just like when you have to find the area. So this is not hard to see. These 2 points, this point is at 2, and this point is at -2. So these 2 points, and this y value is 4 here, and so this point is 2, as you can see that this point is what? This point is 2, 4. If you like, you can write it down. But make sure, make everything clear. When you do these kind of problems here, make everything absolutely clear. I like very clear solutions. The more clear, the clearer solutions are, the more points you will get. And I do prefer very clear solutions. Again, let me remind you, I like very clear, extremely clear, ultra clear solutions so that I don't have to figure out, okay? If I see this and I can see exactly what's going on at no time, then that means you'll get more points. If I have to figure out what's going on, then that is the beginning of problem. That means you'll start losing points. Again, if I have to figure out what's going on, that itself will be a negative. Is that clear? The easier time you give me, the more points you get. That's a very general rule. Okay, so now we get this. Now let's see. So this is the base. That is the base. Now, whose parallel cross sections perpendicular to the y-axis? Oh, this time we now cut into slices where each slice will be perpendicular to the y-axis. Therefore, now this is the y-axis right here. That means we'll be cutting slices like this. Let me maybe use my red marker now. Red. So I'm going to cut it like this at cross-section Y. So if you take a cross-section Y, what happens here? Then what crossing Y are squares. When you take a cross-section of Y, perpendicular y-axis, then you get squares where one side lies in the base. So this guy, when you cut it here, what happens is the square is going to stick out. So now let me take the cross-section here. And this segment right here will be this segment right here. And of course, what that really means is the square is actually going to stick out like this. To stick out like this is actually going to stick out vertically up. I cannot draw this three-dimensional picture here, but the square is not going up there. It's actually sticking out towards us, perpendicular to the monitor. Okay, perpendicular monitor. It's sticking out this way. It's vertically up. So now let me erase that. So the best thing to do is, since this is a two-dimensional plane, I mark the segment there, and then I separately write AOY like this. Where that segment right there is this segment right here, and the square is going to stick out. So what is the shape going to be? I think the shape is going to be something like this. Something like this. And then it's this right here. And then this, oh yeah, you know what? This kind of reminds me of a TV. I don't know. Have you ever seen TVs which are 30 years old? Have you? These are what? They're called the brown tube TVs. Have you seen brown tube TVs, class? Have you seen brown tube TVs? Well, if you know what these brown tube TVs are, you know what that means. That means you're old. Okay, that's what it means. Okay, if you do not recognize what these are, if you've never seen these guys, then that's a good thing. That means you're young. Okay, that's what it is. So anyway, brown TVs are like a TV, and then the behind is like it's very thick. Okay, and they usually have that kind of shape there. But anyway, that's what it is. So we cross it this way, and the squares are standing up this way, so mark this here. So now let's figure out. So let's see. What is the main axis here? The main axis is the y-axis. The main axis is the y-axis. So in this case, what is the splicing direction? The splicing direction is now dy. Very, very important. And once the splicing direction is dy, that means everything on the diagram must be in terms of y. All the x's must be in terms of y. So now the question is, what is ay? The splicing direction is dy. Splicing direction is terribly important. If your splicing direction is wrong, then you are going to mess up. If your splicing direction is wrong, you have no chance of getting the integral correct. Is that clear? It is that simple. If the splicing direction is incorrect, you have zero chance of getting the integral correct. You have no chance. So this is very important here. X, y-axis, the main axis. We're cutting into slices perpendicular to the y-axis. That means this will be dy slicing. Again, y-axis, sometimes I'm going to write this as what? As x equals 0. X equals 0 is the main axis. Actually, for volume by cross-sections, the main axis will always be x-axis or y-axis. You are not going to see x equals -1 or x equals -2. They will be the same as x equals 0, which is the y-axis. So now let's see what we have here. So this guy is y equals x squared, right? Okay, so what is this point here? This point here, cross-section y. And now what that means is this is y here, y. And now what's x? X is, so now from here, what's x? Oh, x is equal to plus minus square root of y. So it looks like we get into this, because we need to write everything in terms of y. So that means y. That means this guy here is what? Oh, you know what? Let me rewrite this one more time. So this point right here, let me write this one more time here. This guy right here, this point, is going to be y. Y coordinate is y. What's x? X is going to be plus square root of y minus square root of y. Well, this guy will be square root of y. Why? Because this part of the curve is what? Is x equals square root of y. And then this part of the curve is what? Is x is equal to minus square root of y. Because in this case, x value is negative. So this point is square root of x, square root of y, comma y. What is this point right here? This point right here, what is that point? That point is going to be, what? Is going to be, how about this? I guess I don't have to put arrow there. Let me just write it out. This is going to be what? This is going to be minus, the y point is y, obviously. This is cross-section y. And then the x point is now between minus square root of y. With this. Oh, that's what that is. So now, how do you find the distance? Well, how do you find the length of that segment? Well, the length of the segment is the distance between that point and that point. So the y points are exactly the same. So we take the difference of the x coordinates. We always go right minus left. So that one, it comes out to be 2 times square root of y. Basically, square root of y minus square root of y. So there's a double negative here. Watch out for these double negatives. So that means this length is 2 square root of y. Now this is square. That means this must be also 2 square root of y. So now what is a of y? A of y will be 4y. Now y is, now what is this? Now look at these slices here. These slices here. Y is the ranges from y equals 0 to y equals 4. So this is from 0 to 4. This is a of y. What is a of y? A of y happens to be very simple in this case, 4y. That's it. So this time the integral is much easier. If you calculate this, what do you get? 4. So yeah, we get 2. You know what? If you calculate this, we get, let me just write down the 4 here. And when you integrate y, we get half y squared. So let me write half y squared. This is times here. So now half y squared. And now we can what? We can evaluate this from 0 to 4. What is this here? So that will be 4 times half times, and then a 4 squared. So that's 16. So it looks like this is going to be what? 32. 32 what? 32. Well, there's no units mentioned here, so I guess it's 32. If I give you the units, then you have to give me the units here as well. But here, no units are given, so no units. But the unit will be something squared. Will be the unit of area, of course. Okay? Whatever the unit of y is, this is the unit of y squared. So it will be like, if this is inches, then this will be inch squared. So this is what? This is the end of 2a and 2b. Okay, let me now save this. Let's save this. Try to do one more. Yeah, we have a lot of problems here, by the way. Equal odd triangles. In this case, we have equal odd triangles here. right? If it's equilateral triangle, what is an equilateral triangle? Equilateral triangle, this is essentially the same problem here, but in this case, we have an equilateral triangle like this. So we have a segment like this. All of you know how to find the area of an equilateral triangle? Okay? If this, let's say if the base is, let's say C, let's say for example, if this is C, then how do you get the area of this equilateral triangle? Equilateral triangle here. That means this guy is going to be C over 2. And then this height right here is this is C. This is C over 2. And the height is going to be what? This is going to be square root of 3 over 2 and then times C. So what is the area of this guy? The area of this guy is equal to what? The area of this guy is equal to half times base times half times base, the C, and then times height. It's square root of 3 over 2, C. And C. And then this, therefore, this is equal to square root of 3 over 4. Then C squared. Okay, here I just reviewed the area of an equilateral triangle. Okay, so that's the only difference here. So whatever the C is, basically the area will cross the area will be this guy right here. That's it. And then if you look at example 4, same thing. Y projection of this guy here, and then we have right isosceles triangle, where right isosceles triangles whose hypotenuse lie in the base. So let's say in this case we have the segment here. Now in this case, how does the diagram look like? It's a right isosceles triangle whose hypotenuse, that means the triangle is going to look like this. Now, it could be a possibility that on some other problems you might actually have this, and then it's a right isosceles triangle like this. But if it's this, they will not say that whose hypotenuse lie on the base. If I change this word hypotenuse to a leg, again, class, this example 4, I keep everything the same. If I change this hypotenuse to a leg, then that means the cross-section is going to look like this. Here the hypotenuse, where the hypotenuse lie on the base, this one is where a leg lie on the base. So every little word here completely changes the problem. It's not just X and Y, okay? So you have to be very, very careful with everything here. Every little word is very important here. If you misinterpret, then you might lose almost all the points. Okay? So be very, very careful when you read these kind of problems here. I'm going to save it. Clear? Do you have any other problems here? Let me see. Y equals 0. Y equals 0. Okay, how about if you do, let's say, what if you try example 7? Let's try example 7. Find the volume of the solid whose base is a circle of radius 4 and whose parallel cross-sections perpendicular to the base are squares. Okay, what is this? Let's try this one. Example 7. Get this. And then what is this here? You know what? Let me, how about if I draw the circle first? That will make it easier. So let me draw a circle first. Then I'm going to draw the two axes here. So we have this. So now we're trying to first, when you have any kind of problems like this, first we want to get the base correct, and then they'll talk about the cross section. Okay. So this is the volume by cross section, the volume by simple cross sections. The cross sections will be limited to rectangles, right triangles, equilateral triangles, isosceles triangles, circles, a semicircle, quarter circle. It will be limited to these only. If the cross section is more complicated than that, then that will be covered in Calc 3, where you deal with three-dimensional geometry. Okay, so the continuation of this section, you actually get into Calculus 3. That is, if any of you will be taking Calculus 3. If you do not take Calculus 3, then I guess you're not going to continue on this topic. Okay. Okay. So now let's look at this here. What is this? We have what? We have XY axis here. So now let's go back here. Let me read the whole thing again. Find the volume of solid whose base is a circle radius 4. Okay, we got that. So this is now this entire circle is now the base in this case. Sometimes not the entire circle is the base. Sometimes only the quarter circle is the base, or sometimes the semicircle is the base. So just because you have circle doesn't mean that whole thing is real. In this case, it's solid whose base is a circle. In this case, it does say it's a circle, not a semicircle, not a quarter circle. The radius 4, so we got the base here, and whose parallel cross section perpendicular to the base. Actually, in this case, it doesn't matter whether it's x-axis or y-axis. So in this case, x-axis or y-axis, no difference. X-axis, or y-axis, no difference because it's a circle. So in this case, what is it? Perpendicular to the perpendicular to the x-axis, and or in this case, the perpendicular y-axis. To specifically, we would write it this way, but in this case, it doesn't really matter because it's a circle. Okay, so perpendicular to the x-axis or perpendicular y-axis, same thing in this case. So in this case, what we'll do is, if you have a choice here, why don't we just make x-axis the main axis? Okay, because it's x-axis the main axis, so we cut the item this way. I cannot show you. Okay, but when you cut a carrot or cut something something long, then this is the way you cut it. We cut it to the x-axis. So perpendicular x-axis. So why in this case, why don't we just say that we are going to cut it this way? So just think that we cut it through perpendicular x-axis. And so we'll be cutting it this way. You'll be cutting it this way, and we'll be cutting it this way. Okay? Now, perpendicular x-axis are squares. Okay, are squares. So if you cut it this way at x, let's say we cut at x. Let's say we cut at x here, then we get this segment right here. Now the slicing the main axis is x-axis. The slicing direction is dx. So now if you cut here, then what is the cross section? The cross section are squares. Okay, so we look like we get a square. You know what? Let me go it over here. Get a square. Where the base right here is actually this segment right here. That segment right there is that segment right there. The actual solid, the square is kind of sticking out like this. The square is sticking out vertically. Okay, it's not like that. It's a three-dimensional object. Its object is sticking out like this. Okay, so that's how it's going to stick out. If you do that, then how will the curve look like? The curve actually is going to look like this. The surface that we have here. And then we select all these points here. And then we have all the select like that here. It's kind of weird solid, okay, something like that. But when you make a cross section, the cross section will always be a square. Okay. So that's how the solid is going to look like. It's kind of hard to draw a three-dimensional solid in a two-dimensional screen. Okay, so anyway, that's what you get. But this is good enough. When you do these kind of problems here, you don't need to draw a three-dimensional picture. All you have to do is draw the XY plane, and then separately write a cross section. So in this case, the slicing direction is dx. So this will be our A of x. That will be our A of x. So now let's go back here. Main axis. What is the main axis? In this case, we get to choose. X-axis, Y-axis, they have the same thing anyway. So that's why they said perpendicular base. It doesn't really matter which way they cut it. X-axis, dy slicing, dx slicing, they're exactly the same in this case. So in this case, the main axis is the x-axis. If the main axis is the x-axis, then what is the slicing direction? The slicing direction is, in this case, let's go by dx. Again, in this case, dx slicing, dy slicing, they're exactly the same. And so now, that means everything has to be written in terms of x. X here. And this guy is x here. X here. That means everything has to be written in terms of x. So now let's look at this point right here. What is this? Now this is a cross section at x here. What is this point right here? This point will be cross section x, so this will be x. X times, what is the circle here? Oh, the circle equation is this. X squared plus y squared is equal to 4. Now, we have to express everything in terms of y, so what we get is this y here. Y is equal to plus or minus 4 minus x squared. And the question is, do we need that plus minus? Yes, we do. Now, what is that top circle? What is the top half circle? The top half circle right there, that is actually what? That is actually y is equal to square root of 4 minus x squared. What is the bottom half circle? Bottom half circle is what? Is y is equal to minus square root of 4 minus x squared. Is this. So now that point is what? That point is square root of 4 minus x squared. Now this bottom point right here is x comma minus square root of 4 minus x squared. What is the length of that segment at cross section x? That will be 2 times square root of, that'll be what? 2 times the square root of, 2 times the square root of 4 minus x squared. Then this side is the same thing, because it says that it's a square. If it says something else, then of course this side will be something else. In this case, that is exactly what it is. So in this case, this is a of x. What is a of x? A of x, again, what is it? This is from minus 4 to 4. This is for, again, let me say this, okay, let me write this in black. The limits are from minus 4 to 4. The slices will lie between, from x equals negative 4 to 4. So this is from negative 4 to 4. And what is a of x? A of x will be 4 times, or what? 4 times, yeah, you know what? Let me just, instead of simplifying, let me just show you what it is. 2 times square root of 4 minus x squared. And then the whole thing squared. And when you square this, there will be no more square roots. So the integrand is actually going to be very simple. Not only that, note that this guy is actually an even function again. And from negative 4 to negative 4 on a symmetric interval like this, from negative 4 to 4. So can you apply the even odd property of definite intervals? Yes, we can. You can apply that one too. And so the value of the interval is actually much easier than what you think. Okay? Okay, you know what? Let me not do example 1 since we don't have that much time. The pyramid, you know what? Okay, let me, you know what? How about this here? I'm going to save this and then clear this. Let me just go back to our pyramid here. The pyramid is actually going to be like this. Is, what is this here? Well, no, example 1. Let me talk about example 1. Example 1 is L and H here. You know what? Let me, yeah, this one, should I do this right now? Yeah, you know what? I'm sorry. Don't have too much time. Let me skip the pyramid. Okay, let me skip the pyramid. So, actually, a of x in this case, if you, let me make some comments about this, annotate. So when you make it like this, and then make this, and then make the pyramid stand this way, like this. So the slicing direction is what? Is this. This is our height h, so this is the h. And this is our L right here. And this is actually y is equal to, this graph right here is y is equal to, what is it, h. So this is actually equal to L over h, x. At this side right here. So what is this here? Main axis is x. L of x happens to be this L of h. over x, and then x, and then square this guy. And then the interval is actually going to be from 0 to h. So copy this guy right here. L squared over h squared over x squared. This is x. This is equal to, what, x? H squared? Oh yeah, this is going to be 1/3 h squared, 1/3 h squared, 1/3 L squared, and then times h. This is what you get at the end. You know, don't worry. This example one, I'm not going to ask you, this is not covered on the final, okay? Since we ran out of time. I don't have enough time here. So this one, just, you know, if it's good for you. If you understand this, then that's good. That's a good thing. So don't try to avoid it. If you're a good student, then, you know, you can try this. But again, yeah, this pyramid, a little bit tricky here because they don't really tell you what the base is and all that. They describe you the solid, and you have to come up with this description. So that's the hard part. So example one is actually more difficult than example 2 through 2, 3, 4, 5, the rest of it, because they don't tell you exactly what it is, but they describe it. They don't give you literally, but they describe it for you. So whenever they give description, it tends to be a little more difficult because you have to set it up. You have to formulate what the base is and what the area is and so on. Okay? All right, so let me stop here. It's almost time. I think we have only 4 minutes left. Today's the last day. All of you have a good day and good semester. And looks like I don't have much time here. However, if any of you have any questions, I will try to answer all of your questions. Okay? So I will be here. I think I already made some comments at the beginning of the the class, and it's on the it will be posted on the on the screenshot. Okay, you can look it up. But hey, again, the most of the important topics will be on the final, and especially I am planning to give you at least a few problems on volume and on area. If 5.1 and 5.2 are never covered, so whatever I covered today and yesterday, it will be covered on the final exam. Again, at least one problem in area, at least one problem volume, might be more than one. So altogether, on chapter 5 might be about 2 or even 3 problems. And I'm planning to give about 10, so that's a heavyweight, right? So make sure that you know the area and the volume and cross-section and the disk method. Okay, so I guess I have to stop here. If any of you have any questions, then you can ask me. Again, this is the last meeting. No more meeting now, and I will not be communicating with you. So this is it. Okay. Well, it was a good class, and I hope all of you will have a happy final. And for your grades, how long will it take for your grades to be posted? Just give me about 3 days. Okay, so 3 days, because it takes more, and I have to put more care on grading your final exam. Many times, I will be looking at 2 times, okay, instead of just once, just to make sure that everything is fair and graded correctly. So I cannot afford to make any mistake on the final, grading the final and assigning your scores, okay? So it will take much more time. Okay, so all of you have a good day, and any questions before we start the Zoom meeting?
Oh, yeah.